be able to control all these factors, under all modes of operation, car manufacturers have developed computerized control systems that can monitor engine performance, tailor fuel and spark delivery to match performance demands, and control emission systems to minimize the level of pollutants in the exhaust. The three basic components of a computer control system are a microcomputer, sometimes called a microprocessor, control module, or control unit, sensors, and actuators. Sensors supply the microprocessor, or control module, with input on engine conditions. Microprocessors, or control module, analyze this data from the sensors and calculate a response to these conditions. Actuators are used to adjust engine operation, after receiving a signal from the control unit, to a relay, or solenoid. The sensors, actuators, and computer communicate through the use of electronic circuits. For example, if a coolant sensor signals the computer the engine is getting hot, the computer will generate an output command to turn on the cooling fans by grounding the relay circuit that controls the fans. Let's discuss these input sensors, and look into what they do and how they affect the engine. Coolant temperature sensor. The engine coolant temperature sensor is very important because its input is used to regulate many engine functions. It can activate or deactivate the early fuel evaporative system. It controls the open, closed-loop feedback modes. During open-loop mode, the coolant temperature sensor controls air-fuel mixture until the engine warms up and goes into closed-loop mode where the oxygen sensors will take over. It controls the startup fuel enrichment on fuel-injected engines. It controls the spark advance, or spark retard. Spark advance is often limited until normal engine operating temperatures are met. While the engine is cold, EGR flow is blocked. The coolant temperature sensor prevents canister purge until the engine is warm. It also controls the throttle kicker or idle speed and controls the transmission torque converter clutch lockup. The coolant temperature sensor is typically located in the head or intake manifold. It screws into a water jacket. On most systems, the coolant temperature sensor is a variable resistance thermistor. On older systems, a switch coolant sensor may be used. This type of sensor may be designed to stay closed within a certain temperature range or to only open when the engine is warm, 125 degrees Fahrenheit or hotter, for example. Because of the major role in triggering so many engine functions, a faulty coolant temperature sensor or sensor circuit can cause a variety of problems. The most common is the failure to switch to closed-loop mode when the engine is warm. It can cause poor cold idling, a rich fuel mixture or stalling due to a rich fuel mixture, retarded timing, or a slow idle speed. It could cause a cold hesitation or stumble due to no EFE or early fuel evaporation or even EGR flow that is occurring too soon. Poor fuel mileage due to a rich fuel mixture, open loop operation or a retarded spark. Also, always check for wiring faults, corroded connectors, and proper temperature range thermostat. Barometric pressure sensor. This sensor alters the air-fuel mixture and timing controls depending on the altitude in which the vehicle is being operated. Manifold absolute pressure sensor. The function of the MAP sensor is to sense air pressure of vacuum in the intake manifold. The engine computer uses this information as an indication of engine load to adjust the air-fuel mixture and spark timing. The MAP sensor reads vacuum and pressure through a hose connected to the intake manifold. A pressure-sensitive element in electronic circuit generates a voltage signal that changes in direct proportion to pressure. MAP sensors measure manifold air pressure against a pre-calibrated absolute pressure. Because it bases its readings on preset absolute pressure, MAP sensor readings are not adversely altered by changes in operating altitudes or barometric pressure. The air temperature sensor is a thermistor, sometimes called an air change or manifold air temperature sensor. Resistance decreases as manifold air temperature increases. Resistance will increase as manifold temperature decreases. The control module measures the voltage drop across the air temperature sensor, then uses this input to help calculate fuel delivery. On some vehicles, an ambient air temperature sensor is used to control the vehicle's automatic climate control system for passenger comfort. The air conditioning demand sensor is a pressure switch that signals the computer control module that the AC clutch is cycling. The computer will use this data to determine engine load and control engine idle speed. On some engines, idle speed can be altered to prevent hesitation. The engine position sensor. This sensor informs the computer the speed of the engine, and when the piston in each cylinder reaches top dead center. This input is used to set engine timing and fuel injection delivery. While there are several distinct types of position sensors used, all communicate with the computer by generating a voltage signal by using a Hall effect switch or electromagnetic induction. Other names are distributor pickup coil, crankshaft or camshaft position sensor, or profile ignition pickup sensor. Mass airflow sensor. This sensor measures the flow of air entering the engine. This measurement of airflow is a reflection of engine load, throttle opening and air volume density. It is similar to the relationship of the engine load to map or vacuum sensor signal. There are several different types of mass airflow sensors used: throttle position sensor, or DPS sensor. Engines with electronic fuel injection, or feedback carburetors, use a TPS sensor to inform the computer about the rate, or throttle, opening and the relative throttle position. A separate idle switch or wide open throttle switch may be used to signal the computer when these throttle positions exists. The TPS is a variable resistor that changes resistance as the throttle opens. As the throttle plate opens, the computer enriches the air-fuel mixture to maintain a proper air-fuel ratio of 14.7 to 1. The most common symptom of a bad or misadjusted DPS is hesitation or stumble during acceleration because the computer won't receive the proper signal, telling it to add fuel, causing it to stumble. Vehicle speed sensor. This sensor tells the engine computer the vehicle speed in miles per hour. This sensor also controls when the torque converter clutch locks up, and can be used to control EGR flow and canister purge. NOx sensor. The NOx sensor tells the engine computer if the engine is panging. In turn, the engine computer will retard the timing. The NOx sensor is a piezoelectric device that converts engine knock vibrations into a voltage signal. Some engines can adjust, retard, timing on individual cylinders. Oxygen sensors, or O2 sensors. The exhaust gas oxygen sensor, or lambda sensor on some vehicles, is the key sensor in the closed-loop mode. One type is made with a zirconium dioxide element that generates a voltage signal proportional to the amount of oxygen in the exhaust. It compares the oxygen content in the exhaust with the oxygen content of the outside air. As the amount of unburned oxygen in the exhaust increases, the voltage output of the sensor drops. O2 sensor output ranges from 0.1 volts, lean, to 0.9 volts, rich. A perfectly balanced air-fuel mixture of 14.7 to 1 produces an output of around 0.5 volts. When the O2 sensor reading is lean, the computer enriches the air-fuel mixture. When the sensor reading is rich, the computer leans the air-fuel mixture. The O2 must be hot to operate. Some O2 sensors are equipped with an internal heating element. This helps reach operating temperatures quicker and maintains temperature during periods of idling or low engine speed. The second type of oxygen sensor does not generate a voltage signal. It acts like a variable resistor, altering a base voltage supplied by the control module. When the air-fuel mixture is rich, the sensor resistance is low. When the air-fuel mixture is lean, the sensor resistance increases. Variable resistance sensors do not need an outside air reference. They offer very fast warm-up, and operate at lower exhaust temperatures. The normal lifespan of this critical sensor is typically between 30,000 to 50,000 miles. They can be affected by air leaks in the intake or exhaust manifold. A misfiring spark plug that allows unburned oxygen to pass into the exhaust can cause the sensor to give a false lean reading. Vacuum sensor. Vehicles that do not have a map or barometric sensor may use a vacuum sensor to provide engine load and speed change information. The vacuum sensor measures the difference between atmospheric pressure, outside air, and engine vacuum. Power steering switch or PS switch. This switch causes the engine computer to raise the idle speed when the power steering is turned to lock, as far as it will turn right or left. This prevents stalling during tight turns or when parking the vehicle. System battery voltage. This voltage provides power for the system. Poor grounds can cause all or parts of the computer-controlled system to malfunction. High gear switch. This sensor supplies the computer with the information on when the automatic transmission is in high gear and allows the torque converter clutch to lock up. Brake switch, which is an on/off switch. This input signals the control module to disengage the torque converter clutch. It can also lower idle speed on some vehicles. The brake switch will also disengage the cruise control. EGR valve position sensor. Car manufacturers use a wide variety of sensors or switches to determine when the EGR valve is open. This information is used to adjust the air-fuel mixture. The exhaust gases that recirculate via the EGR valve into the intake manifold reduce the available oxygen, requiring less fuel, resulting in low hydrocarbon levels in the exhaust. Computer outputs and actuators. Computer outputs are electronic signals to control devices or actuators. These actuators perform the mechanical movements, or actions, that change the operating conditions of the engine or vehicle. The following are the major actuators in a computer-controlled engine. Air management solenoids. Air bypass and diverter solenoids control the flow of air from the air pump to either the exhaust manifold, open loop, or the catalytic converter, closed loop, canister purge solenoid. This solenoid controls when stored fuel vapors in the canister are drawn into the engine and burned. The computer only activates this solenoid when the engine is warm and above idle speed. EGR flow solenoids. EGR flow is controlled by a pair of electronically controlled vacuum solenoids. One supplies manifold vacuum to the EGR valve when the EGR valve is required. The second one vents vacuum when the EGR is not required. Fuel injectors. These solenoid valves deliver the fuel spray in the fuel-injected systems. Idle speed controls. These actuators are small electric motors. On carbureted engines, this idle speed motor is mounted on the throttle linkage. On fuel-injected systems, a stepper motor, sometimes called an idle control valve, is used to control the amount of air bypassing the throttle plate. Other solenoids. Computer-controlled solenoids may also be used in the operation of cruise control systems, torque converter lock-up clutches, automatic transmission shift mechanisms and many other systems where mechanical actions are needed. Ignition module. This is actually an electronic switching device triggered by a signal from the engine control module, or engine computer. Motors and lights. Using electrical relays, the computer is used to trigger the operation of electric motors, such as the fuel pump, or various warning lights or display circuits. System operation. Control loops are the cycles by which a process can be controlled by the information received from input sensors, engine computer ROM, computer processing, and output of specific commands to control actuator devices. The basic purpose of all computerized engine control loops is the same. To create an ideal air-fuel mixture of 14.7:1, which allows the catalytic converter to operate at maximum efficiency, while giving the best mileage and performance possible, and protecting the engine. Closed loop mode. Closed loop is basically the same for any automotive system. Sensor inputs are sent to the computer. The computer processes them, and sends out commands to the output devices. The output devices adjust timing, air-fuel ratio, and emission control operation. The resulting engine operation affects the sensors, which sends new messages to the computer, completing the cycle of operation. This complete cycle is called closed loop, often referred to as feedback systems. The sensors are constantly sending information to the computer on what is taking place. This allows the engine to make constant decisions and changes to the output commands. Open loop mode. When the engine is cold, most electronic engine controls go into open loop mode. The computer does not react to feedback information. It relies on pre-programmed information that allows basic ignition timing, or air-fuel settings, and disregards some sensor inputs. The open loop mode is activated when a signal from the temperature sensor indicates the engine temperature is too low for gasoline to properly vaporize and burn in the cylinders. Some O2 systems may go in open loop while idling, or anytime that the O2 sensor cools off enough to stop sending a signal, and at wide open throttle, fail-safe, or limp in mode. Fail-safe is nothing more than the computer's attempt to take control of vehicle operation when input from one of its critical sensors, such as map, throttle position, or coolant temperature sensor has been lost. Fuel control systems. Fuel injection systems. Typical inputs to the engine computer consists of manifold pressure, throttle position, engine speed, crankshaft position, engine temperature, and oxygen in the exhaust. The computer processes this information and tells the fuel injectors how long to stay open. This system controls the air-fuel ratios much more precisely than any carburetor system. The constant sensor inputs and precise fuel control provide a very accurate air-fuel mixture. Emission control systems. There are three main emission-controlled devices that are controlled by the engine computer. They are the EGR valve, air pump, and the evaporative emissions canister. The computer keeps the level of three major pollutants, CO, HC, and NOx at acceptably low levels. Other emission control devices may be fully or partially controlled by the computer, include thermostatic air cleaner, early fuel evaporative devices, and electric choke, control of non-engine functions. Some devices that are not directly connected to the engine are also controlled by the computer to ensure maximum efficiency. Example, air conditioner clutches can be turned on or off, depending on various conditions. One common control procedure turns off the compressor when the throttle is fully depressed, allowing maximum engine acceleration by eliminating compressor load. On some vehicles, the torque converter lockup clutch is applied and released by a signal from the engine computer. The computer controls electrical solenoids that will allow transmission hydraulic pressure to lock up the torque converter clutch.